Hi everyone, so this video is continuation of the previous video only, although the title of this video will be Friis equation, but before studying Friis equation we need to study a lot of things as well. After that we will move to Friis equation. So in the previous video what did we study? We studied about some parameters of antenna. First we studied about radiation intensity, then average radiation intensity, then we studied about directive gain, then directivity, then efficiency and then power gain. So all these terms are interrelated to each other and we saw the relation between all of them. Also, we understood one thing, that if this is your P in, then how much power it will radiate? The power radiated will be P radiated, right? Just one second. Yeah, it is fine now. So power radiated will be P radiated. If P in is given at the source, then it doesn't mean the complete power will be radiated. Some power will be lost in the transmission line as well. So what is your P radiated? P radiated is neta into P in. Now from P radiated, from the antenna, if I take R distance, from antenna if I take R distance, so at the distance R, what you can find? At the distance R, what you can find? Can you find P radiated here? No. At the distance R, what you can find? You can find P average. Now in this chapter, what we will do? In the previous chapter, there was only one antenna. In previous chapter, there was only one antenna. Now in this chapter, there will be receiving antenna as well. Like this antenna is transmitting EM wave energy and this antenna is receiving EM wave energy. When I told you the definition of antenna in very first lecture, what did I say? If I give VI, it should give me EH. And if I give EH, it should give me VI. What was the definition of antenna? If I give VI, give me EH. If I give EH, it should give me VI. So now to the receiving antenna, what I will do? I will give EH. Here, what will come? Here, EM wave energy will come. So I will give it EH. And what it will give me at the load? At the load, it will give me VI. So what is the definition of antenna? If I provide voltage and current to the antenna, it should give me EM wave energy. And if I provide EM wave energy to the antenna, it should give me voltage and current. So now my target would be to understand that what I will be getting here, how much power I will get at the load. This is my target, that's it. From here I will send some power P in. This antenna is at some distance R. How much power I will get at the load. This is the motivation of studying this lecture. So till now we have seen that there will be losses in antenna, all those things will come into action. Now a few more losses will also come into action and a few more terms will come into action. So till now we have studied that from if this is P in, then here we will get P radiated and at the distance of R from the antenna, from the transmitting antenna, I can write down my P average. And what is that P average? That P average is known as P radiated upon 4 pi R square into directive gain. Also, I told you this 4 pi R square will come only if you are taking the complete range of theta. If you are taking the complete sphere. If you are taking the complete sphere, that means the range of theta is from 0 to pi. Then only 4 pi R square will come. If you are taking hemisphere, then 2 pi R square will come. Right? So, till this point we have studied. Now, the job of receiving antenna will come. That how the receiving antenna will take the power. How it will take the power. The transmitting antenna will radiate the power. Now, this will take back the power now. Receiving antenna has the job of taking the power. So how it will take the power, that we need to study. So before that you need to understand wave polarization. This topic we have already covered. Like sometimes some teachers cover this topic in antenna. So if you have studied EM wave from somewhere else, then you might not have studied wave polarization. So if you have studied wave polarization, then it is fine. If you haven't studied wave polarization, then go back to the playlist and study this particular topic. Wave polarization. This will be used in our video. So now the first term which we are going to introduce is known as polarization loss factor. What we are going to study now? Polarization loss factor, PLF. So what do you mean by that? So what our antenna will radiate? It will radiate EM wave energy, right? Our antenna will radiate EM wave energy. Now polarization is defined with respect to electric field only. Radiation pattern is defined with respect to electric field. In the same manner, polarization is also defined with respect to electric field only. So let's just say from this antenna I am getting an EM wave and the component of electric field is dancing in Z direction. This is what I am assuming. Or let's just say it is dancing in X direction. I am assuming that from my antenna EM wave got out and in this EM wave there will be electric field, there will be magnetic field. So electric field component is dancing in X direction. So it is polarized in X direction, right? I can say that my EM wave, my transmitted EM wave is polarized in X direction. This is what I can say. Now, when it reached to the receiving antenna, when my EM wave reached to the receiving antenna, then what happened was my electric field was dancing in X direction as well, and now it is dancing in Y direction as well. So what will be the equivalent? The equivalent will be like this. Are you getting this point? What I am saying? When it went out of the transmitting antenna, then it was dancing in X direction. That means it was polarized in X direction. And when it reached to the receiving antenna, at that time it is dancing in X direction as well. It is dancing in Y direction as well. So it is polarized in XY direction. So from here to here, polarization got changed. You will say that, sir, this is also linearly polarized. This is also linearly polarized. Yes, linear polarization is the same, but direction got changed. No, here electric field was in X direction. Now it is in XY direction. So if your direction is changing, if your electric field direction is changing, or if your polarization is changing, or you can say if there is some polarization mismatch, then polarization loss factor will come into action. When it will come into action? When there is a polarization mismatch. Are you getting this point? So what does this polarization mismatch represent and where it will be used? That we will see certainly. In this video only we will see it, but let's just build a formula. So what I have written, polarization loss factor, PLF. It will come into action when there is a mismatch between the polarization of the transmitted wave and the received wave. Is that fine? Now what I am saying is that my transmitting and receiving antenna have polarization in PT direction and PR direction. What I mean to say is that my transmitted electric field, it will have some magnitude and it is dancing in PT direction. This is what I am saying. And my received electric field, this is my transmitted electric field and this is my received electric field. Okay. Transmitted electric field means whatever that is coming out of transmitting antenna. And what do you mean by receiving electric field? Whatever that is coming into the receiving antenna. So my receiving electric field will have some magnitude and it is dancing in PR direction. T for transmitted, R for received. Okay. So how my polarization loss factor will be defined? It will be defined as mode of PT dot PR square. This is how it is defined. Mode of PT dot PR square. Just you need to take the unit vector of the transmitted wave and then you need to take the unit vector of the received wave. Okay. And then just do the dot product and take the square of that. Can you let me know how I can write it down? What will be the dot product of two unit vectors? Magnitude 1 and the angle between them. Magnitude 1 and the angle between them. So what will be the answer? Cos theta square. This is my polarization loss factor. So there are two formula of polarization loss factor. This is the first one. This is the second one. Now this was our transmitting antenna and this was our receiving antenna, right? So what did I say? That from here my electric field was dancing in X direction, and when I got here my electric field is dancing in X direction and Y direction. So this is one of the possibility when polarization loss factor can come into action, right? This is one of the possibility when polarization loss factor can come into action. So what will be the polarization loss factor here? AX cap dot, because this is the transmitted wave. And what about the received wave? Received wave is AX cap plus AY cap. But certainly you will divide by under root 2 as well. Why is that so? Because you need to take the unit vector. What is this? This is the unit vector. So AX cap plus AY cap divided by under root 2 and then take the whole square. So what you will get? 1 by under root 2 whole square. So what will be the answer? Half. So polarization loss factor will be half. So this is one of the possibility. We will solve the problems. I am just telling it. Now what I am saying is that this is my transmitting antenna. Now my receiving antenna is placed somewhat like this. Or how I can make it? It is placed somewhat like this. This is how my receiving antenna is placed. So now what I am saying is that electric field is not changing its direction. Electric field is dancing in X direction only. In the previous case, what was the scene? That it was electric field was changing its direction. In the previous case, I said that electric field is changing its direction. Now I am saying that electric field is not even changing its direction. But the angle of transmitting antenna is different. Like receiving antenna is like this, but transmitting antenna is like this. And now electric field is dancing in X direction only. But when it will strike the receiving antenna, it will not strike it parallelly. Are you getting this point? From here, it went out parallelly. Electric field went out parallelly. But now your receiving antenna is placed something like this. So there is some angle between transmitting and receiving antenna, right? Previously, the angle was 0. Both were parallel to each other. But now the receiving antenna is like this. This is your transmitting antenna. So now there is an angle between transmitting and receiving antenna. So this theta is the angle between transmitting and receiving antenna. Are you getting this point? Or you can say it is the angle between the transmitted wave and the received wave. This is also possible. Or you can say it is the angle between transmitting antenna and receiving antenna. What I mean to say is that your polarization loss factor can come into action if your transmitting and receiving antenna are not parallel to each other. If they are at some angle, then also it can come into action, even though electric field is not changing its direction. Are you getting this point? Okay. So all kind of questions we are going to see. So let's start problems. So very simple problems can be asked on this particular topic, but till now I don't think any question has been asked on this particular topic. In GATE examination they did not ask it, but certainly it can come. But in ISRO and in BARC and in ECE examination, a lot of questions are there on this particular topic. So this is ISRO question only. So electric field of EM wave is given by, this is the incident electric field, and it is incident on an antenna. So that electric field is given as AX cap plus AY cap by this. You need to find the polarization loss factor. So what will be my polarization loss factor? So if I write down what is my incident, or you can say transmitted, so that is AX cap. And what is the direction of received? That is AX cap plus AY cap divided by under root 2. I am talking about the direction. So this will be the direction, right? So dot product I need to do now. Divided by under root 2. Then whole square. So what I am getting, AX cap dot AX cap, that will be 1. AX cap dot AY cap, that will be 0. So 1 by 2, 1 by under root 2 whole square. So your polarization loss factor is 1 by 2. So this is the answer. And if I need to find it in dB, what will be the answer in dB? Tan log tan 1 by 2. Right? It will be 3 dB, but let's do it in the calculator. 2 log tan tan. Although we remember this answer, but 3 dB. Okay. So polarization loss factor can also be minus 3 dB. It can be found in our dB as well. And why did I take 10? Why not 20? Because already there is a square, no? Whenever in any term square is coming, then you take 10 log 10. If square is not coming, then you take 20 here. Let's just say for voltage. If something is in voltage and you convert it into dB, then what do you do? 20 log 10. If there is current, then what do you do? 20 log 10. But if there is power, then what do you do? 10 log 10. Because what is power? Power is V square by R or I square into R. So square is already there, no? That's why you do 10 log 10 in case of power. So square is already there, no? So now you will do 10 log 10. In all the things like directivity, indirective gain, in all those things, what we were doing when we were calculating in dB? When we were calculating it in dB, what we were doing? We were doing 10 log 10 because all these are associated with power, right? So that's why. And in complete antenna, you will always take 10 log 10 only. Never you will have to take 20 log 10. Because all the calculation we do with respect to the power. Because our main concern is how much power we are getting. This is our main concern in antenna. So this is minus 3 dB and polarization loss factor is half. So quickly you do the solutions, okay? Now what is the polarization loss factor when a linearly polarized antenna receives a circularly polarized wave? Okay? Linearly polarized antenna receives a circularly polarized wave. This should be written there. So what is my transmitted wave? You can write down PT or you can write down AT. It depends on you. So what is the direction of my transmitted wave? Any linearly polarized you need to take. Any linearly polarized wave you need to take. So in linearly polarized wave, what is the condition? That your phase difference should be multiple of pi. Do you remember this thing? It could be 0, it could be pi, it could be 2 pi. Let's just say AX cap. Is this linearly polarized? Yes. AY cap? Yes. AX cap plus AY cap? Yes. AX cap minus AY cap? Yes. Minus AX cap plus AY cap? All these are linearly polarized. And what about circularly polarized? What about circularly polarized? In circular polarization, the phase difference has to be the 2n plus 1 pi by 2. Plus minus can also come. That means it should be odd multiple of pi by 2. It could be pi by 2, 3 pi by 2, 5 pi by 2, 6, 7 pi by 2. In that manner it could be. So AX cap plus JAY. Is this circularly polarized? Yes. AX cap minus JAY. Is this circularly polarized? Yes. AY cap plus JAX. Is this circularly polarized? Yes. So any random two example you can take. I am taking AX cap plus AY cap. Any two random you can take. You will get the same answer only. What I am taking? AX cap plus AY cap. I will solve it by taking two examples. Do not worry about it. So this is my transmitted. And what about the received one? Received I am taking as ax cap plus j axy. Okay. This is what I am taking. Now what I need to do? Polarization loss factor. I hope you understand the meaning of this j. This j is just a phase. When I calculate the magnitude, okay, this is the unit vector. Really sorry. This is unit vector. So I cannot write down ax cap plus ay cap. Ax cap plus ay cap divided by under root 2. This will be your transmitted wave. And what about the received wave? This is your circularly polarized. Right? So what will be the magnitude? Will it be 1 square plus j square? No. This j is just a phase. We have proved it in time average pointing vector. If you remember, I gave the complete derivation. I converted from phasor form to time domain form, and then I told you it is just a phase. It will never come into action when we are talking about the magnitude. So this j will never come into action if I talk about the magnitude. So what will be the magnitude here? Under root 1 square plus what is the multiple of j? That is 1 only, plus 1 square. So magnitude will be under root 2 only. Right? This we have already seen in our time average pointing vector. So I am not doing the derivation here. Ax cap plus jy under root 2. This I can take. So what will be my polarization loss factor? So my polarization loss factor will be 1 plus j divided by under root 2. Or if you are not understanding like this, then I will write completely ax cap plus ay cap under root 2 into ax cap plus jy divided by under root 2 whole square. Right? So what you are getting? Ax cap dot ax cap. What that would be? 1. Ay plus jy. What that would be? 1 plus j. Under root 2 into 2. 2 whole square. What you are getting? Under root 2 divided by 2. What is the magnitude of 1 plus j? Under root 2 only, no? 1 plus j. Magnitude of 1 plus iota b. Under root a square plus b square. So that is under root 2 divided by 2 whole square. So again what you are getting? 1 by 2. Right? Now let's take another random example. You might be confused that, sir, what if I had taken, sir, what if this is my linearly polarized wave? This is also a linearly polarized wave. And what about the received wave? Let's just say I take this as something like this. Say yes or no. Can I take in this manner? This is my received wave. This is my transmitted wave. So what will be my polarization loss factor? That would be ax cap dot ax cap minus jy divided by under root 2. So 1 into 1, what that, and whole square is also there. So ax cap dot ax cap, what that would be? 1. Ax cap dot ay cap, that would be 0. So 1 by under root 2 whole square. What you are getting? 1 by 2. So always answer will be same. No matter whatever the example you take, whether you take this example or you take this example, answer is always going to be 1 by 2 only. So if your transmitted wave is linearly polarized and received wave is circularly polarized, whether it is right hand circularly polarized or left hand circularly polarized, always your polarization loss factor will be coming half. So these kind of statement wise question can come. Are you getting this point? So these statement wise questions can certainly come. Now what is the polarization loss factor when two antennas are rotated by angle 30 degree? So now they are having a angle difference of 30 degree. So they are rotated by 30 degree. You need to find it in dB2. So what will be the answer? Polarization loss factor, that would be cos theta square. So cos 30 square, what that will be? Under root 3 by 2 square. That would be 3 by 4. So if I need to find it in dB, what that would be? Tan log tan 3 by 4. So 0.75 log tan into 10 minus 1.24. One more fact is there, that is here what is the value of polarization loss factor? 3 by 4. So what do you think, what will be the range of polarization loss factor? What will be the range of polarization loss factor? From 0 to 1, no? Say yes or no? Because what is the range of cos theta? That is minus 1 to 1. But what you are doing, you are taking the magnitude, also you are taking the square. So what will be the range? 0 to 1. Polarization loss factor is just mode of cos theta square. So the range will be from 0 to 1 only. So these kind of small statement wise question can come in ECE or in your BARC. In gate examination, that is very rare. Like if they want to frame a question, then they will frame a MSQ. In first statement, they will write what is the range of polarization loss factor. In second statement, they will write that this is your incident, this is your reflected wave, then this much polarization loss factor will be there. This statement they can write, or they can say that my incident wave is linearly polarized and received wave is circularly polarized. Then what will be the polarization loss factor? So these kind of questions they can frame in gate examination. In MSQ only they can frame these kind of questions. Okay. I did not connect the mic. And now I'm not sure whether my voice came or not. So first I need to check if my voice came or not, and if it came, then it would be very bad. So I need to modify it. So let me pause the video once. Yeah, hi guys. So I'm back now. So I just checked that mic was not connected. Although the sound came, but the quality of the sound wouldn't have been that good. So for last 20 minutes, the sound quality was not that good. But from now onwards, the sound will be good only because I have connected the mic. Okay. So let's proceed in our video. So what did we show here? The polarization loss factor would be from 0 to 1. Now if you calculate polarization loss factor for this particular question and for this particular question, let's calculate polarization loss factor. So what that would be? This is the transmitted wave. So transmitted wave is polarized in x and y direction, and the reflected wave is also polarized in x and y direction only. Right? Square you need to do. Ax cap dot ax cap is 1 plus ay cap dot ay cap is 1 divided by under root 2 into under root 2, 2 whole square. So what you are getting? Polarization loss factor is 1. Let's check this example. What will be your polarization loss factor here? Incident. What is the incident wave? Ax cap plus ay cap divided by under root 2. Sorry, I should not say incident, I should say transmitted. This is the transmitted wave. What about the reflected wave? Ax cap minus ax cap, sorry, minus ay cap divided by under root 2 whole square. So that would be ax cap plus ax cap 1 plus ay cap minus ay cap minus 1 under root 2 into 2, 2. So what is the answer? 0. So what is polarization loss factor? That is equals to 0. So here also polarization loss factor is 0. Here it was 1, here it is 0. So this is known as condition of no mismatch. And this is the condition of complete mismatch. Okay. Complete mismatch. So when you get polarization loss factor equals to 1, that is the condition of no mismatch. That means this is what you want. You want your polarization loss factor to be 1. Whatever that is transmitted, same is received. The direction of polarization, the polarization the polarization of transmitted wave and the received wave, both are same. Here both are at the angle of 90 degree. You can calculate the angle between them. The angle is 90 degree. So polarization loss factor is 0 and here it is 1. So you want your polarization loss factor to be 1. So this is the condition of best case. This is the condition of no mismatch. And no mismatch means this is the best case. And this is the condition of complete mismatch. So these kind of statement wise question can come in your examination. Okay. That this is the condition of complete mismatch, this is the condition of no mismatch. So these statement wise question can be coming in your examination. In the gate examination, they can frame some options and then they will write which of the statement is true. So these kind of questions can be coming. Okay, let's solve this question. So here what do you see? The transmitted and received, both EM waves are same polarized. Transmitted wave is also circularly polarized and received wave is also circularly polarized. Say yes or no. But calculate polarization loss factor now. Now this is not the unit vector. This is just the direction. Okay. This is not the unit vector. So I need to write down unit vector as well. So what will be my polarization loss factor? That would be ax cap plus jy divided by under root 2 because I need to write down the unit vector dot ax cap plus jy divided by under root 2. Ax cap dot ax cap 1. Jy dot jy will be j square. Right? J into j will be j square. Ay dot ay will be 1 divided by under root 2 into 2, 2 whole square. 1 is 1. What is j square? Minus 1. divided by 2. So what is polarization loss factor? 0. That means what we are getting? Worst case. So if I say that my transmitted and reflected wave are polarized in the same direction, then my polarization then my polarization loss factor will be 1. Is that statement correct? Let me pause the video. I need to, I'm finding it difficult. Yeah, so what I was saying, if our transmitted and reflected wave are polarized in the same direction, then my polarization loss factor will be 1. Here transmitted and reflected wave were in the transmitted, sorry, not reflected, transmitted and received. Really sorry. Here my transmitted and received EM wave were polarized in the same direction. So what was my polarization loss factor? 1. Here my transmitted and received EM wave, again they are polarized in the same direction. Now what is my polarization loss factor? 0. So you cannot conclude anything from here. But if I say that my transmitted and received EM wave both are same polarized and both are linearly polarized. Transmitted and reflected waves are linearly polarized and both are polarized in the same direction. Then you can say that your polarization loss factor will be 1. So whenever these statement wise questions are coming, no, so every time you will take some example. What you will do, you will take example. Let's just say in the examination I have written down the statement that if your transmitted wave is linearly polarized and your received wave is circularly polarized, then your polarization loss factor will be 1. If this is the statement written, then what you will do, you will take an example of linearly polarized. Any wave Ax cap is linearly polarized. Then you will take the example of circularly polarized. What it could be? Ax cap plus Jy divided by under root 2. Then you will calculate the polarization loss factor. What it will come out to be? 1 by 2. So that statement would be no. So better than mugging up any statement, we will take examples always. But if I say that angle between two antennas is 90 degree in the like this case, what is the polarization loss factor when the two antennas are rotated by 30 degree angle? If two antennas are rotated by 90 degree angle, then what will be the polarization loss factor? Cos 90. What is cos 90? 0. So polarization loss factor will be 0 at that time. And if both are parallel to each other, if both antennas are parallel to each other, then what will be the polarization loss factor? Both antennas are parallel to each other. So what is the angle between them? 0 degree. Cos 0 is 1. So at that time polarization loss factor will be 1. So these kind of statement wise question can come in your examination. Till now, very rarely any question has been asked. I don't think any question has been asked on polarization loss factor in GATE examination. Then sir, why did we study it? We studied it for ISRO examination and ECE examination. Along with that, it will be used in our next concept. Our next concept is the concept of aperture area. So what do you mean by aperture area? So what is this? This is your receiving antenna. What is this? This is your receiving, RECE. Okay, whatever the spelling is, RECEIVE. RECEIVE. I teach aptitude as well, so my vocab has to be strong. But in aptitude, I never teach vocab. I only teach the quantitative part. Okay, so this is the receiving antenna. So now receiving, what is the job of receiving antenna? To take the EM wave energy. So from some transmitting antenna, some EM wave energy would be coming. Now some EM wave energy can pass like this as well. No? So this antenna is having a area like these are the arms of antenna. No, these are the arms of antenna. So these are the arms of antenna. So antenna can take only EM wave in this direction only. It cannot take EM wave which is passing upward. It cannot take EM wave which is passing downward. So it has a certain aperture area. No, this is known as aperture area. So actual physical cross section area of antenna that is available to receive the radiated EM wave energy. So to receive the radiated EM wave energy, that is the area that is available, that is known as aperture area. So this is the definition of aperture area. Okay. So the area could be anything. The area could be anything. I am making it circular. Okay. I am making it circular, but it could be anything. It's not necessary that it will be circular only. It is not necessary that it will be always circular. It could be anything. And if it is a circular, if your aperture area is circular, if your aperture area is circular, then it is known as parabolic reflector antenna. Reflector antenna. Okay. Like this antenna could be anything. It could be Hertzian dipole antenna, it could be half wavelength dipole antenna, it could be full wave dipole antenna, it could be anything. But your aperture area is circular. If your aperture area is circular, then it is known as parabolic reflector antenna, a very important term. Like sometimes in the questions this term can be written. So you should be what you would be thinking, that we are taking our aperture area to be circular. Is that clear to you? Okay. So aperture area of a receiving antenna is known as AP. AP, aperture area. Okay. So this is how I show it, aperture area. Now in antenna what happens is that this complete area is also not available to absorb the energy. Like this complete area, let us say this is the area of your receiving antenna. This is the area of your receiving antenna. So now this complete area will not be effectively absorbing the radiated energy. Radiated energy would be coming, but complete area will not be effectively absorbing the radiated energy. Are you getting this point? Like here, the energy distribution will not be same. Like on all the point of the area, on all the point of the circular area, it is not necessary that EM wave energy, the intensity of EM wave energy would be same. Or it may happen that your complete area is not available, your complete area is not effectively available to absorb the EM wave energy. So whatever the effective area is available to absorb the EM wave energy, that is known as effective aperture area. What that is known as? Effective aperture area. So what was the first term? The first term was actual physical cross section area. The first term was, like, it is very confusing for the student. So we will focus on it completely. So this is the actual physical cross section area. Actual. Focus on this term. So this is the actual area that is available. Now effective aperture area means the area that is effectively capturing power from incoming EM wave. The area that is effectively capturing power from incoming EM wave. So that is known as effective aperture area. Now there is a certain formula of this effective aperture area. What is that? Lambda square upon 4 pi directive gain into polarization loss factor. Sometimes in the textbook you will find that only this much factor is given, but that is wrong. Polarization loss factor also comes into action. So this is the formula of effective aperture area, which is very, very important. You need to keep in mind, no matter what happens, lambda square upon 4 pi into directive gain. Now there is another term that is known as maximum effective aperture area. Maximum effective aperture area. So what you are going to do, you just need to take the maximum of aperture area, maximum of effective aperture area. Maximum effective aperture area, maximum effective aperture area means you just need to take the maximum of this value. So what will be the maximum of this value? That would be lambda square upon 4 pi into maximum of this into polarization loss factor. So this will be a constant quantity because this will depend on the wavelength of EM wave. This is also pure polarization loss factor that will depend on the polarization. So what maximum you can see? Maximum of GD theta comma phi. And what is the maximum value of directive gain? That is directivity. So what is the formula of maximum effective aperture area? That is lambda square upon 4 pi into directivity into polarization loss factor. So what is the summary of everything that we have studied? First we studied about polarization loss factor. You understood, like incident wave polarization dot, transmitted wave polarization dot received wave polarization. Do the dot product and take the magnitude and take the square. That's it. This is our polarization loss factor. Now coming to the aperture area. So this is our antenna. Antenna is having a particular area that is available for capturing EM wave energy. That is known as aperture area. Now this complete area will not be effectively absorbing the energy. This complete area will not be effectively absorbing the energy. So the area that is available to effectively absorb the energy, the area that is available to effectively capture the energy, that is known as effective aperture area. So formula for that is lambda square by 4 pi into directive gain into polarization loss factor. Anyway, you need to keep in mind there is no shortcut of that. Now maximum effective aperture area. What is this maximum effective aperture area? So this maximum effective aperture area is coming out to be maximum of effective aperture area. So what is the maximum of effective aperture area? That would be lambda square by 4 pi into directivity into polarization loss factor. Okay. So you see this formula. In both of the formulas, is there any dependency on efficiency? No. Neither your effective aperture area neither your maximum effective aperture area is depending on efficiency, because directive gain doesn't depend on the efficiency. Power gain depend on the efficiency. What is power gain? This is your power gain. So power gain will be depending on efficiency, but directive gain never depends on the efficiency. So your effective aperture area and maximum effective aperture area never depends on efficiency. So this point I have written, the effective aperture area or maximum effective aperture area. The effective aperture area and maximum effective aperture area does not depend on the efficiency. Is that clear to you? Okay. Now there is a relation between aperture area, that was AP, and maximum effective aperture area. What is that relation? So efficiency into aperture area is equals to maximum effective aperture area. Not very important, so I am not putting star mark, but if you want to remember it, you can remember it. What is the relation? Efficiency into aperture area is equals to maximum effective aperture area. Mark this point, very important. This formula would be wrong. Neta into AP is not equals to effective aperture area. No, this is wrong. This formula is wrong. What is the correct formula? Efficiency into aperture area is equals to maximum effective aperture area. So don't get confused. Till now what we have seen, what you need to keep in mind. What is aperture area, you know. What is maximum effective aperture, what is effective aperture area, that also you know. What is maximum effective aperture area? Just maximum value of this aperture area, that's it. Now there is a relation between AEM and AP. So first term and last term both are having some relation. What is that? If you multiply the efficiency with aperture area, you will get your maximum effective aperture area, that's it. Very rarely, like there is 0.1% chance that it will be used somewhere, but still if you need it somewhere, then you might be asked some question in the examination based on this particular topic. Okay, but certainly these two are very important. These two will be highly used. So certainly we can write down summary. Like there is no summary. First we studied about polarization loss factor, then one formula we understood, that is effective aperture area, lambda square by 4 pi GD theta comma phi polarization loss factor. Now where it will be used, so that we need to see. So let's just say from here P radiated was coming. From here P radiated was coming. From some antenna P radiated was coming. So at distance R, can you write down P average? Yes. At distance R, I can write down P average. Now at distance R, let's just say there is some receiving antenna. So this receiving antenna is getting P average. This receiving antenna is getting P average power density, right? This P average power density will be incident on this receiving antenna. What is this? This is your receiving antenna. Receiving antenna. So some power was radiated by the transmitting antenna, then at distance R it became P average. Now this P average will be incident on the receiving antenna. So from this receiving antenna will take some time average pointing vector. It will take some power density. Now if it takes some power density, that is P average, then how much power it will transmit? How much power it will transmit to this transmission line? What I mean to say is that here it was P average. What is the unit of this P average? That is watt per meter square. The unit of this P average is watt per meter square. We call it power density. So if P average power density is incident on the aperture area of your antenna, then how much power you will get after the aperture area? That means here how much power you will get. So what will be this Px? This is your power. This is your power. How much that power would be? What is this? This is power density. What is this? This is power density. So P average power density is coming, that is incident on receiving antenna. Now after the aperture area to the input of the transmission line, after the aperture area to the input of the transmission line, how much power is being incident? Here to the input of transmission line, just after this aperture area, how much power is there? So that power will be a very important formula, that would be P average into aperture area, not maximum effective aperture area, not simple aperture area. This is your effective aperture area. So that power, this Px power will be P average into aperture area. Sorry, again I am saying aperture area. This is your effective aperture area. So this P average, this power will be P average into aperture area. Basically from here watt per meter square was coming, right? This was watt per meter square. That will be multiplied with the area. So what it will become? Watt only, no? So this is a unit of power. This is a unit of power. So you are having a receiving antenna, some P average power is coming, that will be incident on the aperture area of your receiving antenna. But P average will be multiplied with what? Aperture area? No, it will be multiplied with effective aperture area. Why is that so? Because effective aperture area is capturing the power effectively. The complete area is not available to capture the power, only effective aperture area is available to capture the power. So till this point what we have seen, that we will have some P in, from this P in some power will be radiated, at some distance R we will have some P average. Now if I know this P average, then how much power will be getting in, that is your Px. So can I write down this Px? Yes. So from the beginning of the lecture, what we started with? We started with radiation intensity. So if I have the radiation intensity, then from here I can get the P radiated. Because what is P radiated? That is your u theta comma phi sin theta d theta d phi. From there you can get P radiated. Or if you are having P in, then from there also you get P radiated, because there will be transmission line. So there will be some losses. The losses could be conducting losses, it could be dielectric losses, or it could be reflection losses. So how much power will be radiated? P radiated. Then at distance R, how much power density would be reaching? That power density would be P average, and that would be P radiated upon 4 pi r square into directivity. Directivity of what? Directivity of the transmitting antenna. Directivity of the transmitting antenna. So till this point we have solved already. Now what is the new term that we studied? The new term that we studied was effective aperture area. So if P average is multiplied with effective aperture area, then it will give the power inside the receiving antenna. So inside the receiving antenna, this much power is going. Now how much power will be reaching here? So again there will be losses. What losses could be there? In the transmission line, what all losses could be there? Conducting loss, dielectric loss, and reflection losses. So then eventually we will be receiving some power here. Are you getting this point? So this was the complete summary of whatever that we have studied. So where all the formulas will be used, I hope that is clear. Usually what people do is that they mug up the formula, that this is what is happening, then eventually this much power will be coming, and they will mug it up. And if they mug it up, they will just get confused that where I will need to multiply polarization loss factor, where I will multiply neta, where I will multiply efficiency, where I will like a lot of factors are there. But I hope now path is clear to you, and this path is known as Friis equation. So instead of studying directly Friis equation, we have studied small component of Friis equation, and in the end now this Friis equation will not seem difficult to us. Say yes or no. And we can write down other formula of this one as well. So what will be this Px? So this Px power would be, what is your P average? Your P average is P radiated, that is coming from here, divided by 4 pi r square into the directive gain. Directive gain of what? Directive gain of a transmitting antenna. So directive gain of a transmitting antenna, right? What about this A? A is lambda square by 4 pi into directive gain. But directive gain of what? Receiving antenna. Why receiving antenna? Because aperture area is associated with this antenna, and this P radiated is associated with what? It is associated with your transmitting antenna. So there is another transmitting antenna as well, which I did not make. So here theta comma phi, along with that polarization loss factor will also come into action. So usually people mug up this formula, and if you mug it up, then eventually you are going to mess it up in the examination. So no need to mug up anything, your path is clear. So what kind of questions can be coming into the examination? This kind of questions can be coming into the examination. That from here this much power is going, P in power is going, your Z in is 75 ohm. Basically this antenna is providing 75 ohm resistance. So I will tell about this particular question, but before that let's see a very important relation. What is that? So first write down the formula of effective aperture area, lambda square by 4 pi into the directive gain into polarization loss factor, and here lambda square by 4 pi into directivity into polarization loss factor. So lambda, this depends on the source. right? Or it will, or you can say it is depending on the frequency of EM wave. What about polarization loss factor? That will be simply incident and reflected. That will depend on the polarization. So from here, can I say that my effective aperture area is proportional to the directive gain? Say yes or no. Effective aperture area is proportional to the directive gain. And secondly, you can say maximum effective aperture area is proportional to the directivity. Say yes or no. Is that clear to you? So this relation can be used to solve some problems. Okay, this can be used to solve some problems. Let's solve this question. This is known as Friis equation. So, but rather than writing formula, we will see the concept. Okay, because formula will not be asked anywhere. We need to know the concept. So better let's understand the concept. What is the concept? That from here P in power is going. Then this is having Z node impedance. This transmission line is having Z node characteristics impedance. The input impedance of this antenna is 75 ohm. The loss resistance of this transmission line is 25 ohm. And the directive gain of this antenna is 22 dB. So this is your transmitting side. Now at the receiver, this your transmission line is having Z naught of 50 ohm, loss resistance of 20 ohm, and directive gain of 18 dB. You need to find the power delivered to the load, and the load is of 100 ohm. Try doing it on your own. Answer is written. You know every single thing about it. Every single thing you know. So what will be your first task? First task will be to find this P radiated. Then if P radiated travels down, and if it reaches here, what it becomes? P average. That is your power density. Then what will happen? It will be multiplied with your effective aperture area. Then you will get this power. How we are showing this power? That is your Px. Now this Px will go through some losses, and then finally we will get our P load. Power delivered to the load, right? So P load. So what is my power delivered to the load? So from where I will start? I will start from P in. So this is my P in, that is 100 watt. I will start from P in, that is 100 watt. Now, how many losses are there? One will be the loss because of this loss resistance. And how much loss will be there? R radiated upon R radiated plus loss resistance. Do you remember this formula? Say yes or no. R radiated upon R radiated plus loss resistance. We saw the formula based on this, right? So this is the one loss. Another loss will be there. That will be coming because of reflection coefficient. Because this is providing you how much impedance it is providing? 75 ohm. And what is the value of this one? 50 ohm. So what will be the reflection coefficient? The reflection coefficient would be ZL minus Z naught upon ZL plus Z naught. I need to write it down. Upon ZL plus Z naught. That would be 25 by 125. It would be 1 by 5. So what will be the value of 1 minus mod of gamma square? That would be 1 minus 1 by 25. That was 24 by 5. So here the value will be 24 by 5. Say yes or no. Till this point it is clear. So this is the some rough work that we have done. So what is this? What is this much quantity? P radiated. Do you agree to my point? This is your P radiated. From here P in came in, and what will be the P radiated? This is the P radiated. Now what I need to find? I need to find P average now. My next task would be to find P average. So what I will do? P radiated divided by 4 pi r square. P radiated divided by 4 pi r square. So I can multiply by 1 upon 4 pi r square. Same thing. Into the directivity. Directivity of the transmitting antenna. Because P radiated is associated with the transmitting antenna. So into the directivity. What is the directivity? Directivity is 22 dB. Sorry, not directivity, really sorry. Into directive gain. Here I am not going to write directivity. I am going to write directive gain. Both are two different things. So what I am writing? Directive gain. So what is your directive gain? Directive gain of that transmitting side is given as 22 dB. So can I write it down as 10 log 10 GD, that is 22. So GDT is 10 to the power 2.2. So this is P radiated upon 1, P radiated into 1 upon 4 pi r square. What is the value of r? Value of r is 200 lambda. 200 lambda square. Okay. Now where I have P radiated upon 4 pi r square into directive gain of the transmitting antenna, that is 10 to the power 2.2. 10 to the power 2.2 into. So where we have reached? We have found out P average. So this much is your P average. Say yes or no. This much is my P average. So now I have found out my P average. Now the next task. So from P average, now I need to find my Px. So how will I find my Px? So what will happen? It will be multiplied with the effective aperture area of a receiver. So what will be the effective aperture area of receiver? That would be lambda square by 4 pi into directive gain, lambda square by 4 pi into directive gain of the receiver into polarization loss factor, right? So what is the directive gain of the receiver? What is the directive gain of the receiver? That is 10 to the power 1.8. If it was 22, then it was 10 to the power 2.2. If it is 18 dB, that means it is 10 to the power 1.8. So can I write down 10 to the power 1.8 here? Certainly I can write down 10 to the power 1.8 here. Into polarization loss factor. What is the polarization loss factor? 3 by 4. Polarization loss factor is 3 by 4. It can be mentioned in the dB as well. So you can convert as per you. So it would be 3 by 4. So what you have found out now? You have found out Px. So this is your Px. What is your Px? Till this point it is your Px. So what you have found out? You have found out Px now. Now eventually what you need to find out? You need to find out PL. So now what all losses are there? There is loss resistance. If loss resistance is given, what does that mean? There will be, if loss resistance is given, so there will be which loss? Conductance loss it could be, or it could be dielectric loss. So any loss is there. So because of the loss resistance as well, some losses will come into action, and because of the reflection as well, there will be some losses because Z0 is 50 ohm. So your Z0 and ZL are not matched. Since they are not matched, that means there will be losses. So what all losses will come into action? One losses will be because of the loss resistance. So what that would be? This resistance, final resistance. What I mean to say is that when there was a transmission line and it was connected to antenna, then I said that this is my P in and what will be my P radiated. So at that time, what did you say? That P radiated would be equals to R radiated upon R radiated plus R loss into P in. This is what you said, right? Forget about the reflection loss. I am only talking about loss resistance. So R radiated upon R radiated plus loss resistance into P. At that time, what was the explanation given? That I will replace this antenna with R radiated. So from here to here, if I am going, then this is what I am going. This is what I am doing. So from Px to PL, if I am going, so what I can write down? My PL would be equals to R, this load resistance, this RL upon this load resistance plus the loss resistance into Px. Say yes or no. Here your antenna was working as a load. Here 100 ohm resistance is working as a load. Here to here we are going. Now here to here we are going. We are proceeding only, no? Are you getting this point? What I need to find? PL now. So previously I replaced my antenna with 75 ohm. I replaced my antenna with 75 ohm and then I got this expression. Now what I am going to do? Load is already there 100 ohm. So what I will get? Radiation resistance. This is not radiation resistance. Here now it will be load resistance. So 100 upon 100 plus loss resistance, that is 20. That's it. Are you getting this point or not? Okay, so this loss is there and another loss is reflection loss. That you can see that your Z0 and load are not matched. And if they are not matched, that means there will be some losses. Okay. So I hope you must have understood this point, what I wanted to deliver here. So all kind of losses we have taken into action. Like this is the worst case that they can ask. In the examination till now, they haven't asked this kind of worst cases. But this is the worst case they can ask. All kind of factors we have taken into action. Okay, this was your Px. Now final we are finding. So there is radiation, there is a loss because of this loss resistance. So 100 upon, what is 100? 100 is the loss, 100 is the load resistance. So 100 upon 120 into reflection loss. Again we need to take the reflection into action. So this was at the transmitting side. This was at the transmitting side. Now I am finding at receiving side. So what that would be? 100 minus 50 upon 100 plus 50. 100 minus 50 upon 100 plus 50. So that would be 1 by 3. So now how much loss would be there? 1 minus 1 by 9, that is 8 by 9. So loss would be there, that is 8 by 9. So that's it. This is the complete answer. This 100-watt power that we started, it will go through all these of things and then I will receive my P load. Are you getting this point or not? So how you will do the calculation? First thing is that you can eradicate lambda square to lambda square. I will not cut it in the final answer, but here you can see that lambda square and lambda square is gone. So there is no unknown. Now this is complete mathematics. More what you can do is that what this will become 10 to the power 4, 10 to the power minus 2 into 10 to the power 1.8. So this will become 10 to the power 4. So you don't need to solve 10 to the power 2.2. Nah, it will be 10 to the power 4. Now there are a lot of 0 in the denominator, like this is 2 into 10 to the power 4 lambda square. So 10 to the power 4 and this 10 to the power 4 can be cancelled. Basically this and these two zeros can be cancelled because these two zeros will become 10 to the power 4. So smartly you need to do the calculation. Okay, I am just telling you the step of calculation, nothing else. That first step would be my lambda square getting cancelled. Then this 4 pi and 4 pi, this will become whole square, 4 pi whole square. Then I will see 10 to the power 4 I will get here, and these two combined are also getting 10 to the power 4. So that will also be cancelled. Then I can use my calculator and do this calculation. And what I prefer is that I will do step by step calculation. First I will find out P radiated. In the examination I will not be writing this line. My target would be first I find P radiated. From there I will start writing these lines. And always I will put lambda as it is because there is high chance that lambda will be getting cancelled. So when you solve all these things, what you get? Then this number you are getting 63.32 milliwatt. So here all the factors that are required, all we are taking into action, and rather than mugging up any formula for Friis equation, like you see everywhere, every student mug up the formula of Friis equation, but all these things will be written in the examination in statement. And can you find out these things? Certainly you can find out. And this is the maximum limit of Friis equation. Like these are all the losses that can come into action we have taken. All the losses we have taken into action. We have taken polarization loss factor as well into action. So all the losses, every kind of things can be there in the examination. In a gate examination, which question has come is that they did not give this Z naught. They did not give this Z in, I guess, as far as I remember, or they gave this Z in, I don't remember. They did not give this this value. They did not give this loss resistance, and then they asked this question, and they did not give this Z naught value as well. So all these losses, nothing will come into action, right? Basically, if this Z naught is not given, that means they are asking power here only. They are just asking the value of Px. So you just find out Px value. That's it. You don't need to find all these things. If they are not giving you the value of load resistance, that means they are only asking this Px power. That's it. So whatever that is power coming here, that's it. After that, it can go through all other losses as well. That we don't care, right? And if they are saying that there is no loss in the transmission line, that means the transmission line and this antenna are matched, then P in will be equals to P radiated, right? If transmission line and the antenna are matched, then P in will be equals to P radiated, right? And if there is no loss resistance, then there will be no use of this loss resistance, then P in will be equals to P radiated. Then how much distance it will cover, then you can find out P average, then you will simply multiply it with the effective aperture area. That will be your Px and that will be your answer. So whatever that is requirement, that we need to see. Fine. So we will solve these kind of problems, but this is the worst case that can be asked. And if you are able to solve this particular question, then you will be able to solve all the questions of antenna in your gate examination. Only antenna. Till now, if you have studied, till this point, if you have studied our lecture series, then till now you will be able to solve all the question of antenna. There is another topic, that is antenna array. So we will study that. That will hardly take 2 lectures. So after that, you will be able to solve all the questions of antenna array as well. Is that fine to you? Right. Okay then. Yeah, that's it. Now this statement, this is also very important. I will put important. Let me know whether it is true or false. So what I am saying, power received by receiving antenna does not depend on the effective aperture area of transmitting antenna. Did you understand the statement? Like this is my transmitting antenna, and this is my receiving antenna. So
both antenna will have aperture area. No, aperture area is a property of an antenna. It doesn't depend whether it is transmitting or it is receiving. It is the property of an antenna. So it will also have some effective aperture area, and it will also have some effective aperture area. Now what they are saying, power received by the receiving antenna does not depend on the effective aperture area of transmitting antenna. So what will be the power received if I call this as power received? So what will be this power received? That will be equals to P average here. If I know this P average, and from where this P average would be coming, this P average would be coming from P radiated. Let's just say there is no loss. What I am meaning is that there is no loss, or if there is loss as well, then how I will find this PR? What they are saying, power received by the antenna. Power received by the antenna. So this is the power received by the antenna. They are not saying power received by the load. Now what they are saying, power received by the antenna. Power received by the antenna. So now we are not caring about this thing. We are caring about only the antenna. So antenna is receiving this much power. Now after transmission line, what is happening, that we don't care. So I need to write down this PR. So what that would be? That would be equals to neta into P in. What is this neta into P in? That is P radiated. This neta into P in is P radiated. Now what will be P average? That would be 4 pi r square. If I say this distance is r, into the directive gain of the transmitting antenna. Now P average I have found out. What is this? This is your P average. Now what I need to do? I need to multiply the effective aperture area of this one. So lambda square by 4 pi into what is the effective aperture area of this one? That is GD of receiving, or let's write down effective aperture area of the receiving side. That's it, into polarization loss factor. Okay, in effective aperture area only polarization loss factor will come. What is your effective aperture area? Effective aperture area is lambda square by 4 pi into the directive gain of the receiving side into polarization loss factor. So this will be the effective aperture area of the receiving side. So now what do you see? What do you think? That there is no term of, what you will feel is that there is no term of effective aperture area of transmitting side. This is what you feel. But do you think it is correct? No. Why is that so? Because there is directive gain, no? And what did I tell you? What did I tell you here? The directive gain is proportional to the effective aperture area, whether it is from transmitting side or receiving side. If directive gain is there, that means certainly your effective aperture area is also into action. So what I can write down, that my directive gain is, forget about this polarization loss factor. Forget about this polarization loss factor, or you can take this into action as well. So what will be my directive gain? GD theta comma phi. This you don't need to remember, but I just want to write something. 4 pi effective aperture area into lambda square divided by polarization loss factor. So what I can write down here? I need to add a page. So what I can do, I just need to modify this particular expression. So what I am getting, neta into P in divided by 4 pi r square. Now if directive gain of a transmitter, so what that would be? What is the formula that we have developed? 4 pi effective aperture area upon lambda square into polarization loss factor. 4 pi effective aperture area of transmitting side upon lambda square into polarization loss factor. This is your directivity into AER. So what you are getting? This 4 pi is getting cancelled. So whatever the formula you are getting, this neta into P in I am writing as P radiated only. P radiated into effective aperture area of transmitter side, effective aperture area of the receiver side, divided by 4 pi lambda square into polarization loss factor. And r square is also there, really sorry, r square is also there. So that is 4 pi is gone, really sorry, what I am doing. 4 pi is getting cancelled, no? So r square upon r square into lambda square into polarization loss factor. So this is the answer we are getting. So what do we see here? This r is the distance, we don't care. This lambda square is also will be depending on the frequency of EM wave. P radiated that will depend on the efficiency. Polarization loss factor, it will depend on the polarization. So what do you see? That your received power is proportional to the effective aperture area of the transmitter into effective aperture area of the receiver divided by lambda square r square as well, because this distance can also be changed, no, like this is my transmitting antenna, this is my receiving antenna, and if I keep them apart then distance will be increased. I can change lambda as well, but generally like if there is some source then I am not changing that lambda, but it can also be changed. So it depends on the question that what they are asking. So now I will show you a question where this formula will be used, or better just forget about the dependency. This formula can be used somewhere, like in the examination. If they are framing a question, they are telling P radiated, they are telling the effective aperture area of the transmitter side, they are telling the effective aperture area of the receiver side, they are telling you the distance between two antenna, and then they are telling you the frequency of the source, and then they are telling you the polarization loss factor. Then this formula will be used. Do you need to mug it up? No. What you will remember? You will remember the concept, and then from there you can change the expression. Are you getting this point? Do you need to mug it up? No. If you want to mug it up, then you can remember. It is very easy to remember actually. P radiated into effective aperture area of the transmitter into effective aperture area of the receiver divided by r square into lambda square. Just you need to keep one thing in mind, that your power received by the antenna is certainly depending on the effective aperture area of this guy as well. So this you need to keep in mind. Or you can keep in mind is that this P average is also depending on the effective aperture area of this guy. Is this P radiated depending on effective aperture area of this guy? No. P radiated is not depending. P radiated is depending only on the P in and efficiency. But P average depends on the aperture area of this guy. Say yes or no. Very, very important point. These points are missed by the students, even by the educators as well. No offense to anyone, but sometimes these are missed. But intelligently they can frame question from these kind of points. So let's see this question. Consider a wireless communication link between a transmitter and a receiver located in free space with finite and strictly positive capacity. If effective area of transmitted and receiver antenna and the distance between them are doubled, what they are doubling? This they are doubling, this they are doubling, and this they are doubling, and everything else remains the same, then the maximum capacity of a wireless link, maximum capacity of the wireless link, capacity, that means they are asking about received power only. Capacity of wireless link, that means how much power it can receive. This is what they are saying. Or you can say it would be like a ratio of power incident divided by, sorry, it will be ratio of the power received divided by the power incident. What I mean to say is that, what is my power received? Power received will be neta into P in into effective aperture area of the transmitter into effective aperture area of the receiver divided by lambda square into r square into polarization loss factor. So if they are asking capacity, that means they are asking power received by P in. So this is what they are saying, neta into divided by r square plus lambda square. So what is happening? This is getting doubled, this is getting doubled, and if this is getting doubled, then what will happen? This will get 4 times, because it is depending r square. Here the relation is r square, so this will get 4 times. 2 into 2 divided by 4, everything will get cancelled. What will be the answer? Remains same. Effective aperture area is doubled, this is also doubled. 2 into 2, 4 divided by 4, 4 into 4 getting cancelled, remains unchanged. Okay. Two communication antenna A and B, one operating at 300 MHz, other operating at 3 GHz respectively, having same gain, illuminated with identical flux density. Find the ratio of received power. Even if you are not able to solve this one, then also it is fine. What do you think? What is the meaning of having same gain are illuminated with identical flux density? That means there are two receiving antenna. One receiving antenna is receiving antenna A. What they mean to say is that there are two receiving antenna. One is the receiving antenna A, another one is the receiving antenna B. This is receiving antenna A, this is receiving antenna B. Here how much power is coming? P average only, and here also P average is only coming. What they are saying, illuminated with identical flux density or power density, this is what they mean. Then what they are saying, one is operating at 300 megahertz, A is operating at, for this your frequency is 300 megahertz, and for this your frequency is 3 gigahertz. So can I find the value of lambda? Lambda will be C by F. So 3 into 10 to the power 8 divided by 3 into 10 to the power 7. So that would be 30. And can I find the value of lambda here? C by F. That would be 0.3. Okay. What they are asking, find the ratio of the received power. So power received by A divided by power received by B. So P average is same. Don't care about that. P average is same. So P average and P average will be getting cancelled. Then what you need to do? Ratio of effective aperture area of A, ratio of effective aperture area of A divided by ratio of effective aperture area of B. So it will be lambda square upon 4 pi. It will also be lambda square upon 4 pi into directivity into polarization loss factor. Polarization loss factor and polarization loss factor will be getting cancelled. Directive gain. What they are saying? Two communication operating having same gain. Directive gain is also same. That means directive gain of A is equals to the directive gain of B. This is what they have said. So on what value your aperture area will depend? What is the formula of aperture area? Lambda square upon 4 pi into directive gain into polarization loss factor. This guy is gone. This is same. Polarization loss factor is gone. 4 pi is also gone. So what it is depending on? Lambda square. What it is depending on? Lambda square of A divided by lambda square of B. So what that would be? 900, and this is 3 into 10 to the power minus 1. Just one. Yeah, so I was thinking what was the error. So there was this small error. Here it would be 3 into 10 to the power 8. No, this is 3 into 10 to the power 8. So this will be 3 only. This is 0.3. So here what is my lambda A? 3 square divided by 0.3 square. So what will be the answer? Ratio will be 100 ratio 1. Because this will be 9, this will be 0.09. So it would be 100 ratio 1. So answer would be 100 ratio 1. 100 ratio 1. This will be the correct answer. Okay, just very simple thing. We just got to know that your power received is proportional to lambda square, right? It is proportional to lambda square because PR received A divided by PR received B is equal to lambda square divided by lambda square A divided by lambda square B. That means they are proportional to each other. So this is the relation that you understood. Okay. So क्या हो गया भाई? टेढ़ा क्यों लिखा जा रहा है ये? Okay. Let's see the next one. You try solving it very easy. Okay. Not very easy, but you need to use your brain here. You try solving this one. Then you try solving this one. Then this is some of the concept that I need to teach. 2-minute concept it is, nothing else. Then you try to solve. After this only you will be able to solve these questions. So we will see this concept and we will solve these two problems. So you try solving it on your own. I will take a break and then I will start solving it. Okay, you can also take a break. Okay, so let's start this question. A person with the receiver is 5 kilometer away from the transmitter. So this is a transmitter. This is a transmitter. And the person is 5 kilometer away. So the person is somewhere here. So in antenna, whenever you doesn't understand anything, just make the diagram. So he is 5 kilometer away. Now what they are saying, what is the distance that person must cover to further detect at 3 dB decrease in the signal strength? Signal strength should be decreased. So this transmitter would be radiating some power. This transmitter would be radiating some power. So as you increase the distance, as you go in this direction, the power strength will decrease. Why is that so? Because what is the power radiated? Power radiated is R square into P average. Whatever it is, can I write down P radiated would be proportional to the P average? Say yes or no? Because it is R square into P average into sin theta d theta d phi and then integration. So can I write it down in this manner that P power radiated is proportional to the P average? And what is your P average? P average is 1 by 2 neta E theta square. Say yes or no? So can I write it down in this manner that my P average is proportional to E theta s mod of E theta s whole square? And what is my E theta s for any expression? Like for linear dipole antenna, what is that? J I naught upon 2 pi r f theta e to the power minus j beta r anything. What about for Hertzian dipole antenna? IDL sin theta upon, sorry, IDL sin theta upon 4 pi r. So from here what I can see is that my E theta s is proportional to 1 by r. So can I write it down in this manner that my E theta s is proportional to 1 by r. So from here what you will get to know that your P average is proportional to 1 by r square. Then from here what you will get to know that your power radiated will be proportional to 1 by r square. So as the distance increases, my power reduces. At r equals to 0, you will have the maximum power, and as the distance keeps on increasing, the power will keep on decreasing. Now what they are saying, how much distance the person need to go. So person will come here or it will go here. Person will go in this direction only, no? It will cover some distance x because it needs to reduce the power. And how much power it need to reduce? 3 dB decrease. Do you remember what is the meaning of 3 dB decrease? If you have studied network analysis, then you would know. 3 dB decrease means half power. So here power is P. Then what is the power here? P by 2. What is the meaning of 3 dB? So what you can do is that, what I can do, tan log tan into x is equals to 3 dB. I can write down. If here it was 12 dB decrease, then what you would have written? Tan log tan x is equals to 12. So what you are getting? X is equals to 2. That means by the factor of 2 it should decrease. By the factor of 2 it should decrease. What does that mean? That power should be half. So power should be half. So power was P when the distance was 5 kilometers square. And power will be P by 2. Power will be P by 2 when the distance has become 5 plus x whole square. Say yes or no. Did you understand what did I do? P is proportional to r square, no? Power is proportional to, sorry, inversely proportional to r square. So P, power was P when the distance was 5 kilometer. Now power will become P by 2 if the distance has become 5 plus x. That's it. So under 2 is equals to 5 plus x divided by 5. So what is the value of x you are getting? 5 into under root 2 minus 5. 2 into under root into 5 minus 5. 2.07 kilometer. This is the answer. Very easy. Again, let me take a break. Again, I am having something in my throat. Okay, so we are done with this question. Now, it might happen that you are not able to solve this problem. Now, you would be thinking that, sir, we have studied the complete concept and now we are not able to solve the problem. So, I am picking only those problems which you might not be able to solve. There are a lot of problems which you would have been solving very easily. So, those are not picked here. Those I am not solving here. So, it might happen that you are not able to solve all the questions of the assignment or from this video only. Forget about the assignment. It might happen that you are not able to solve all the questions. So I have picked only those problems which is tough for you to solve. Like I am not taking any problem from Friis equation because I know that you know everything about Friis equation. No, you know everything about Friis equation now. If you are able to solve this one, then you will be able to solve a lot of problems on Friis equation. You go and check PYQs of GATE examination. There has been a lot of questions on Friis equation, and you would be able to solve all of them without even remembering a single formula. So that's why I'm not picking up those problems. Okay, so don't be demotivated if you are not able to solve the problem. Just try learning up the concept. Let's move to this one. An antenna in free space receives 2 microwatt of power when the incident electric field is 20 millivolt per meter RMS, the effective aperture area of the antenna. Okay, so this is the electric field value, that is 220 millivolt per meter, or you can write down 2 into 10 to the power minus 2 volt per meter. Okay, effective aperture area you need to tell. So what they are saying, antenna is receiving 2 microwatt power. Antenna is receiving 2 microwatt power. So there would have been some effective aperture area here. So this would have been your P average, and then this would have been the received power. So received power would have been effective aperture area into P average. So what is the received power? That is 2 microwatt. What I need to find? Effective aperture area into P average. What will be P average? E naught square by 2 neta. E naught square by 2 neta, right? But I know E naught by under root 2. What is your ERMS? What is your ERMS? E naught by under root 2. So from here, can I write down in this manner? AE into ERMS square by neta. That is 2 microwatt. So what is your AE here? So AE would be, they are talking about free space, that means neta will be 120. So 2 micro into 120 pi. No, sorry, neta will not be 120, it would be 120 into pi divided by ERMS square. That is 4 into 10 to the power minus 4. So 2 into, this is here 10 to the power minus 6. So if I make it 1.2 pi. So 1 into 2 into 2.4 into pi. 2.4 into pi divided by 4. So 1.88. Yeah. So effective aperture area is coming out to be 1.885 meter square. So if you solve this one, you are getting 1.885 meter square. Very easy question. So P average can be achieved from incident electric field as well, right? Now what is parabolic reflector antenna? That I told you, if the aperture area of the antenna is circular, then it is known as parabolic reflector antenna. Have you seen dish antenna? Dish antenna. Are you having dish TV on your dish TV would be there, no, in your home? Like everyone uses Netflix nowadays. You will use your laptop to watch something. If you want to watch something, you will use your laptop, I know. But if there is some dish TV you would have seen, and then there would be some receiver here. So what happens is that some rays would be coming and that will be taken back by this receiver, and then you get the connection in your TV, and videos are played on your television. So though that is a circular kind of structure, no, dish TV. You can just go and type down dish TV, you will get that kind of structure, and you can go to your roof as well. There also it will be there. Okay. So what I was saying, if the aperture area is circular, then it would be known as parabolic reflector. So can I give that? Can I say that the diameter here is d? The diameter of the aperture area is d. So what will be my aperture area now? The actual area that is available to receive the EM wave energy. The actual area that is available, that would be pi d square by 4. Oh, sorry. That would be pi r square. First I should write down pi r square. And what is r? R is d by 2. So your aperture area would be pi d square by 4. This is your aperture area. What they have given? They have given the efficiency. You need to find the directivity in terms of d, lambda and polarization loss factor. Okay. So what I need to find? I need to find directivity. What I have the aperture area. I don't have effective aperture area. I don't have maximum effective aperture area. I don't have any of these. But I know that what I know that my maximum effective aperture area is proportional to the directivity. That means they have some relation. So what is the formula of maximum effective aperture area? That is lambda square by 4 pi into directivity into polarization loss factor. And what is this equals to? Maximum effective aperture area. That is equals to the efficiency into aperture area. Efficiency into aperture area. Maximum effective aperture area is equals to efficiency into aperture area. Say yes or no. Do I know aperture area? Yes. Do I know efficiency? Yes, I know efficiency as well. That is 0.65. So that's it. Now I can solve it. Neta into pi d square by 4 would be equals to lambda square by 4 pi into directivity into polarization loss factor. So what I need to find? I need to find directivity. So 4 and 4 is getting cancelled. So what I will get? Neta into d by lambda whole square. Look, 4 and 4 is getting cancelled. D by lambda pi square into pi square into 1 by polarization loss factor. This is the formula of directive I am getting, which I don't need to mug up. So let's not keep it in a box. So what I need to do? What is neta? 0.65 into pi square into d by lambda square into 1 by polarization loss factor. So if you calculate this into pi, so you are getting 6.41. So 6.4 d by lambda square into 1 by polarization loss factor. So this is what you are getting. Let me take a pause. Yeah, so this is the directivity you are getting. Okay, 6.4 d by lambda whole square into 1 by polarization loss factor. Now sometimes in the textbook what happens is that in textbook you will find a statement. Which statement you will find? Directivity of polarization, sorry, directivity of what is this? Parabolic reflector. That is d equals to 6 into d by lambda whole square. Okay, this you will find in textbook, and since it is mentioned in the textbook, then these kind of questions can come in your PSU examination or in your ECE examination. GATE will never ask it. GATE will never ask this formula. But in ECE examination, what they have done is that they will give the diameter of your parabolic reflector in terms of lambda. In terms of lambda, they will give that diameter of parabolic reflector and then they will ask you the directivity. So there you need to apply this formula directly. You don't need to do any calculation. But GATE examination will never ask it. But there are a lot of questions in ECE based on this formula. So that's why I taught this concept. In the GATE examination, if they frame question, then they will give the efficiency value as well. Most probably they will give you the lambda value as well. They will try to frame a good question. That means in GATE examination, they will try to frame this kind of question or this kind of question. This kind of question they will try to frame in GATE examination. Okay. So let's try this one first. What they are asking, the mouth diameter of two parabolic antenna are in the ratio, diameter is given. Two parabolic antenna is given. So diameter is given, that is 4:1. Find the ratio of their power gains. Power gain. Find the ratio of their power gain. Power gain here will be equals to directivity only. Because what is power gain actually? Power gain is equals to neta into directive gain. But they did not, they neither mentioned about neta, neither they mentioned about directive gain. They did not mention about everything. They did not mention about efficiency. Neither they mentioned about directive gain. So just treat this as a directivity only. Okay. So your directive gain, what you can see here is that the directivity is proportional to d by lambda whole square. They did not talk about lambda. They did not talk about anything. They just talked about d. So what you need to do? So these kind of questions will be asked in ECE only. And as far as I remember, this is the PYQ of ECE only. Okay. What that would be? What I know is that directivity is proportional to d square. So d square, so 4 by 1 square. So answer would be 16:1. That's it. This is the answer. Okay, but not important for your GATE examination. You don't need to mug up this formula for your GATE examination. But for PSU, ESE examination, for BARC examination, for ISRO examination, these are important. 6d by lambda whole square. Now what about this? At 20 gigahertz, find the directivity of parabolic dish antenna of 1 meter diameter and 70% efficiency. So now good enough data are given. So here you need to derive it completely. What you need to find? You need to find the directivity. So what I know is that K in sorry, not K, efficiency into efficiency into aperture area, efficiency into aperture area is equals to maximum effective aperture area, and that is equals to lambda square by 4 pi into the directivity into polarization loss factor is not given, so forget about that. Polarization loss factor we are taking 1. So this thing can I do in the examination? Yes. The next step what I will be writing, neta into pi d square by 4 is equals to lambda square by 4 pi into directivity. What I need to find, I need to find directivity only, no? So from here what I can see is that directivity will be neta into pi square d by lambda whole square. So what is diameter? Diameter is 1 meter. Diameter is equals to 1 meter. And what is lambda? Lambda is c by f. C by f. What is f? 20 gigahertz. So 2 into 10 to the power 9. Mega giga. Giga is 10 to the power 9 already. So this is 10 to the power 10. So we are getting 1.2 into 10 to the power minus 2. So what is neta? 0.7 into pi square into d is 1 upon 1.5 into 10 to the power minus 2 whole square. So what is the answer you are getting? 100 divided by 1.5 whole square into pi into 0.7. So this answer is too much, but I need to calculate it in dB. Like this we are getting 30,705.03, but we need to calculate in dB. So what I will do, log into 10. So 44.8. Here 45 dB it is written. So what is the answer we are getting? 44.8 dB. Okay. So don't apply any formula. And let's just say if I had applied blindly any formula, let's just say blindly if I had applied this formula, then what answer I would be getting? Let's check. So 6 into what is d? D is 1 divided by 1.5 into 10 to the power minus 2. Because what I what I think is that in dB there should not be much difference. So let's check that. 100 by 1.5 whole square into 6, then log into 10. Here you are getting 44.25, 44.26 dB. So even if you had applied this formula, then also it would be correct by the options, because in the options they would be framing 40, 45, 50, 55. In that manner they would be framing. So you would click on 45 only if you are getting this answer. So luckily you would have been correct in this option as well. But better derive in the examination if they are giving the data of efficiency, because this we have derived for a particular value of efficiency, and this is the general case. Okay, this is the general case. Generally this is the efficiency. Generally this is the efficiency of the parabolic reflector. Yeah, so that's it about our complete antenna. We have covered complete antenna theory. Next chapter we are going to start, that is antenna array. So now we are going to place a lot of antenna. Till now we were studying only one antenna, but now a lot of antenna would be there. So first we will study about 2 element antenna array. So only 2 antenna would be there, and then we will study about n element antenna array. So all will depend that how you place that particular antenna. So all the concept of antenna will be used there. Okay, yeah, thank you very much.